Look up at the night sky. What you see is just a tiny glimpse into the vast, ever-changing canvas of our universe. But here's something that might stop you in your tracks. Every single second, galaxies are racing away from each other at speeds so immense, they defy human comprehension. The universe isn't just expanding, it's accelerating, stretching the fabric of space itself faster and faster with each passing moment. And the strangest part, we still don't fully understand why. This isn't just a cosmic curiosity, it's one of the greatest mysteries of modern science, a puzzle that challenges everything we thought we knew about time, space, and the very fate of reality. Picture this: billions of years ago, all matter in the cosmos was crammed into an infinitely dense point. Then, in an instant, the Big Bang sent everything hurtling outward. But instead of slowing down over time, the expansion of the universe has been speeding up, as if some invisible force is pushing galaxies apart with unstoppable energy. Scientists call this force dark energy, and it makes up nearly 70% of the universe, yet we can't see it, touch it, or even fully explain it. It's as if the universe is playing a game of keep away, revealing just enough to keep us guessing while hiding the rules of the game entirely. That's where today's journey begins. Over the next 30 mind-blowing facts, we'll unravel the secrets behind the expansion rate of the universe, how we measure it, why it baffles even the brightest minds, and what it means for the ultimate fate of everything around us. From the mind-bending role of dark energy to the eerie possibility of a big rip that could tear reality apart, we're diving deep into the forces shaping existence itself. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. In the late 1920s, a quiet revolution unfolded inside the Mount Wilson Observatory, where astronomer Edwin Hubble made a discovery that would shatter humanity's understanding of the cosmos. Peering through what was then the world's most powerful telescope, Hubble noticed something peculiar about the light coming from distant galaxies. It wasn't just faint, it was shifted toward the red end of the spectrum. This phenomenon, called redshift, was the cosmic equivalent of a train whistle dropping in pitch as it speeds away from you. But in this case, the whistle was entire galaxies, and their light told an astonishing story. The farther away a galaxy was, the faster it appeared to be racing away from us. Hubble's observations led to a groundbreaking equation so elegantly simple yet profound. It became the cornerstone of modern cosmology. Velocity equals Hubble's constant multiplied by distance, or V equals h0 times d. This relationship, now known as Hubble's law, revealed a universe in motion, stretching like the surface of an inflating balloon with galaxies as dots on its surface. The implications were staggering. If everything is moving apart, tracing the paths backward in time, meant the universe must have once been compressed into an unfathomably dense point. The first direct evidence for what we now call the Big Bang. But Hubble's work didn't just unlock the past, it gave us a yardstick to measure the cosmos. By calculating how fast galaxies are receding, scientists could estimate their distances, mapping the vast expanse of space itself. Yet for all its clarity, Hubble's law also hinted at deeper mysteries. Why was the expansion rate represented by that critical constant, h0, so difficult to pin down? And why, decades later, would measurements of this constant begin to disagree, sparking what astronomers now call the Hubble Tension? Hubble's discovery was just the first clue in a cosmic detective story that's still unfolding today. Hubble's constant might sound like an obscure scientific term, but here's the thing: it holds the key to understanding the age, size, and ultimate fate of our universe. And right now, there's a cosmic courtroom drama playing out in the world of astronomy, with two teams of researchers locked in a heated debate over its true value. On one side, we have measurements from the Planck satellite, which studied the afterglow of the Big Bang, the cosmic microwave background. and calculated h0 to be about 67 kilometers per second per megaparsec. On the other side, observations of supernova in our galactic neighborhood suggest a faster expansion rate, closer to 73. That gap might seem small, but in the precise world of cosmology, it's a glaring discrepancy. Why does this matter? Imagine trying to predict the exact moment a cake will finish baking, but your oven's thermometer and timer keep giving you wildly different readings. That's essentially the dilemma astronomers face. If the Planck measurements are correct, the universe is around 13.8 billion years old. But if the supernova data is right, it could be younger, throwing everything from galaxy formation to dark energy models into question. This disagreement, dubbed the Hubble Tension, has become one of the most tantalizing puzzles in modern physics. Some researchers argue it might reveal flaws in our understanding of gravity, while others speculate it could hint at entirely new particles or forces at work. The stakes couldn't be higher. Pinpointing h0 isn't just academic, it's about calibrating the cosmic clock. Every time astronomers refine their tools, from sharper telescopes to more sensitive detectors, the tension persists, defying easy explanation. Could there be hidden errors in our measurements, or is the universe subtly changing its expansion rate over time? One daring theory even suggests that dark energy itself might be evolving, growing stronger as the cosmos ages. Until we solve this riddle, the true story of our universe's expansion and its ultimate destiny remains tantalizingly out of reach. Before galaxies, stars, or even atoms existed, the universe experienced something almost too bizarre to fathom. A growth spurt so extreme, it would make today's expansion seem sluggish by comparison. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, space itself underwent a mind-bending phase called cosmic inflation, expanding faster than the speed of light. During this blink of cosmic time, the universe ballooned from smaller than a proton to roughly the size of a grapefruit, smoothing out wrinkles in space-time and setting the stage for everything we see today. This theory didn't just solve one cosmological puzzle, it cracked two of the biggest mysteries in physics. Take the horizon problem. If you peer into deep space in opposite directions, the cosmic microwave background appears nearly identical in temperature, even though those regions were too far apart for heat to have traveled between them in the universe's lifetime. Inflation explains this by suggesting these areas were once close enough to share heat before being violently stretched apart. Then there's the flatness problem, the observation that the universe's geometry is eerily balanced between collapsing and expanding forever. Inflation flattened space-time like stretching a crumpled bedsheet, leaving behind the nearly perfect flatness we measure today. But perhaps inflation's most stunning legacy is what it left behind: quantum fluctuations, tiny ripples in the fabric of space-time. As inflation stretched these microscopic quirks to cosmic scales, they became the seeds for all cosmic structure. Regions where matter clumped slightly denser eventually collapsed into galaxies, while emptier zones became vast cosmic voids. It's poetic, really. The same process that made the universe smooth on large scales also planted the irregularities that allowed stars and planets to form. Without those quantum whispers amplified by inflation, the cosmos might have remained a featureless sea of particles, never giving rise to the rich tapestry of galaxies we call home. Critics initially dismissed inflation as untestable speculation, but modern observations have turned up compelling evidence. The cosmic microwave background's temperature variations match predictions almost perfectly, and the universe's large-scale structure aligns with models of quantum fluctuations stretched by inflation. Yet mysteries remain: what triggered this runaway expansion, and why did it stop so abruptly? Some theories suggest inflation wasn't a one-time event but part of a cyclical process, with pocket universes eternally budding off and inflating spacetime. Whether inflation was a singular cosmic hiccup or part of a grander multiverse, Its fingerprints are everywhere, woven into the very fabric of our expanding reality. Here's the cosmic twist no one saw coming. The universe isn't just expanding. It's doing so at an ever-increasing speed, like a car that mysteriously accelerates when you take your foot off the gas. This bizarre behavior stems from an enigmatic force called dark energy, which makes up a staggering 68% of the cosmos. To put that in perspective, imagine the universe as a vast cosmic pie. The slice we can actually see stars, planets, and galaxies accounts for a mere 5%. Another 27% is dark matter, the invisible scaffold holding galaxies together. The rest, that's dark energy, the dominant but elusive ingredient pushing the universe apart faster and faster. The first undeniable proof of this acceleration came in 1998, when two independent teams studying distant supernova made a jaw-dropping realization. These exploding stars, known as Type Ia supernova, serve as cosmic lighthouses. Their predictable brightness allows astronomers to gauge vast distances. But when researchers measured their light, they found these supernovae were dimmer than expected, meaning they were farther away than standard expansion models predicted. The only explanation, the space between us and those ancient stellar explosions had stretched more than it should have over time. The universe wasn't just coasting on the aftermath of the Big Bang, something was actively speeding it up. Dark energy's discovery flipped cosmology on its head. For decades, scientists assumed gravity would eventually slow the universe's expansion, perhaps even reverse it in a big crunch. Instead, they found the opposite, a cosmos where galaxies are being pried apart by an invisible repulsive force. The leading theory suggests dark energy is woven into the fabric of space itself, a property Einstein once called the cosmological constant before dismissing it as his greatest blunder. Yet, unlike matter or radiation, which dilute as the universe expands, dark energy's density appears constant. As space grows, so does its influence, making it the ultimate cosmic puppet master. But here's where it gets even stranger. Dark energy doesn't just dominate the universe, it dictates its fate. If current trends hold, distant galaxies will eventually accelerate beyond our observational horizon, their light too stretched by expanding space to ever reach us. Billions of years from now, civilizations born in those galaxies would vanish from our cosmic record, leaving behind an isolated Milky Way adrift in an ever-darkening void. Yet despite its colossal impact, dark energy remains almost entirely mysterious. Is it truly a constant force, or could it evolve over time? Could it one day tear atoms apart in a catastrophic Big Rip? Every telescope pointed at the cosmos today is in part a detective tool hunting for answers to these questions, because understanding dark energy isn't just about mapping the universe's past. It's about decoding its ultimate destiny. Imagine a force so relentless it doesn't just push galaxies apart, it rips the universe to shreds atom by atom. This isn't science fiction, it's a chilling possibility called the Big Rip, one of the most extreme futures dark energy could unleash. Picture dark energy not as a steady cosmic pressure, but as a runaway force growing stronger over time. Initially, it would tear galaxies from their clusters, sending them hurtling into the void. Next, stars within galaxies would be wrenched apart, their light fading into isolation. Finally, in the last horrific moments, even atoms, the building blocks of matter itself, would be violently pulled apart, dissolving reality into a sea of disconnected particles. The math behind this scenario hinges on a specific property of dark energy called its equation of state, represented by the letter W. If W is exactly -1, dark energy's density remains constant as the universe expands, the standard model. But if it's less than -1, dark energy becomes phantom energy, gaining strength as space stretches. Like a rubber band pulled too tight, space-time itself would reach a breaking point. Cosmologists calculate this could happen in as little as 22 billion years, a blink of an eye on cosmic timescales. What makes the Big Rip so unsettling isn't just the destruction, but the inevitability. Unlike a big crunch or heat death, there's no gradual fade, just a sudden, violent end where even time loses meaning. Critics argue the Big Rip violates energy conservation laws, but others counter that dark energy already defies conventional physics. Intriguingly, some observations of distant quasars hint at dark energy's equation of state being slightly more negative than predicted, though the evidence isn't conclusive. If true, it would mean the universe isn't just expanding, but bracing for an unfathomable catastrophe. For now, the Big Rip remains a haunting what-if at the edge of cosmology, a reminder that the universe's expansion isn't just a distant curiosity, but a force that could one day rewrite the rules of existence itself. Light doesn't just illuminate the cosmos, it carries encoded messages about the universe's expansion, written in the language of redshift. Picture a galaxy billions of light years away, its starlight traveling across the vastness of space. By the time that light reaches us, something extraordinary has happened. The wavelengths have stretched, shifting toward the red end of the spectrum like a cosmic fingerprint. This phenomenon, redshift, isn't just a color change, it's a speedometer for the universe, revealing how fast distant objects are racing away from us. The physics behind this is both elegant and profound. As space expands, it stretches the light waves traveling through it, much like drawing a wiggly line on a rubber band and then pulling it taut. The amount of stretching corresponds directly to the galaxy's velocity. The greater the redshift, the faster it's receding. Astronomers quantify this shift using the letter Z. A galaxy with Z equals 0 isn't moving away from us at all, while quasars with redshifts above 7, some of the most distant objects ever observed, are hurtling away at over 90% the speed of light. These extreme redshifts act as time machines, showing us the universe when it was less than 1 billion years old. Measuring redshift isn't just about spotting a color change, it's a meticulous process. Scientists analyze spectral lines, the unique barcodes imprinted by elements like hydrogen or oxygen in a galaxy's light. When these lines appear shifted from their usual positions, it's as if the universe itself handed us a ruler marked with cosmic distances. Take the quasar Euler's J1342 plus 0928, one of the farthest known objects with a redshift of 7.5. Its light left when the universe was just 690 million years old, and the stretching of its spectral lines tells us space has expanded nearly 8-fold since then. But redshift isn't foolproof. Dust or intervening gas can mimic its effects, and at extreme distances, relativistic effects complicate the math. That's why astronomers cross-check with other tools, like supernovae or baryon acoustic oscillations, cosmic echoes from the early universe. Together, these measurements form a web of evidence, all pointing to the same astonishing conclusion. The fabric of space is stretching, carrying galaxies along for the ride. Whether observing a nearby spiral galaxy or a quasar at the edge of visibility, redshift remains our most powerful window into the universe's relentless expansion. Here's a cosmic mystery that'll bend your brain. The universe is supposedly 13.8 billion years old, yet some stars appear to be older. How can stars exist before the universe itself? This age paradox isn't just a quirk of bad math. It's a genuine puzzle that's forced astronomers to rethink their understanding of cosmic timelines. Take Methuselah, the oldest known star in our galaxy, whose estimated age once clocked in at a staggering 14.5 billion years. That's nearly 1 billion years older than the universe, according to our best measurements of expansion. It's like finding a 5-year-old photograph of your grandparents holding you as a newborn. Something clearly doesn't add up. At the heart of this paradox lies the way we measure cosmic ages. The 13.8 billion year figure comes from painstaking analysis of the cosmic microwave background, the afterglow of the Big Bang, combined with precise calculations of the universe's expansion rate. But stellar ages rely on entirely different methods, like studying a star's composition and brightness to reverse engineer its lifespan. Methuselah, for instance, is a metal-poor star. Its lack of heavy elements suggests it formed early in cosmic history, before generations of supernovae could seed space with heavier atoms. Initial age estimates placed it impossibly ancient, but updated models accounting for oxygen levels later revised its age downward to around 12 billion years. Still, even this tweaked timeline leaves a hair's breadth between the star's birth and the universe's infancy. This discrepancy forces scientists to confront two possibilities. Either our measurements of the universe's expansion rate are slightly off, or our stellar aging techniques need refinement. The Planck satellite's data, which pegs the universe at 13.8 billion years with remarkable precision, leaves little wiggle room, but stars like Methuselah aren't alone. Globular clusters, dense groups of ancient stars orbiting the Milky Way, also appear suspiciously mature. Their ages hover around 12 to 13 billion years, leaving minimal time for the first stars to form, die, and forge the materials needed for these clusters to emerge. One radical theory suggests dark energy's influence wasn't always constant, that it may have fluctuated in the universe's youth, subtly altering expansion rates and compressing early cosmic timelines. Others propose that gravitational waves or unknown quantum effects could have tweaked the apparent age of ancient stars. Whatever the answer, this paradox isn't just a footnote, it's a reminder that the cosmos still holds secrets, and even our most confident numbers might be hiding a deeper story. Until we solve it, the universe's birth certificate remains tantalizingly incomplete. Deep within the cosmic microwave background lies an extraordinary relic, an imprint of sound waves that once rippled through the primordial universe. These aren't ordinary sound waves, but pressure oscillations moving through a dense, searing plasma of particles, like echoes bouncing through a cavern the size of existence itself. When the universe was just 380,000 years old, this symphony of compression and rarefaction suddenly froze in place as space cooled, leaving behind a cosmic fingerprint known as Baryon acoustic oscillations. Today, these fossilized waves serve as nature's perfect measuring tape, allowing astronomers to track the universe's expansion with unparalleled precision. Here's how it works. In the early universe, photons and baryons, particles like protons and neutrons, were locked in a fierce tug of war. Gravity pulled matter together, while the intense pressure of light pushed it apart. This created regions where matter clumped slightly denser, surrounded by shells where particles had been pushed outward, like ripples around a stone dropped in a pond. The key is that these ripples had a very specific size, about 500,000 light-years across, dictated by how fast sound could travel in that hot, dense medium. When the cosmos cooled enough for atoms to form, releasing photons as the cosmic microwave background, these patterns became permanently etched into the distribution of matter. By mapping galaxies today, astronomers can still detect this signature. Galaxy clusters tend to be separated by a characteristic distance roughly the same 500 million light-year scale, now stretched by cosmic expansion. It's as if the universe left rulers scattered across space, all marked with the same unit of measurement. Surveys like the Sloan Digital Sky Survey have used these standard rulers to measure expansion rates across billions of years. The results are staggering. They not only confirm the universe's acceleration, but provide an independent cross-check with supernova and redshift data, tightening our grip on dark energy's properties. What makes baryon acoustic oscillations so powerful is their immunity to cosmic dust or observational biases that plague other methods. Whether peering at galaxies 7 billion light-years away or analyzing the cosmic microwave background's subtle patterns, the same underlying physics holds true. Recent projects like the Dark Energy Spectroscopic Instrument are pushing this technique further, mapping millions of galaxies to reconstruct expansion history with razor-sharp accuracy. Each measurement is another piece in the puzzle, helping us understand whether dark energy is truly constant or changing over time, a question that may determine whether our universe faces a gentle expansion or a cataclysmic end. The beauty of these ancient sound waves is their silent persistence. They've traveled across 13.8 billion years, carrying encoded information about the universe's youth. Every galaxy distribution map is like a palimpsest revealing layers of cosmic history beneath the surface. As we decode these patterns, we're not just measuring space, we're listening to the echoes of creation itself, a whisper from a time when the entire universe was dense enough to carry sound. And with each new survey, these whispers grow louder, guiding us closer to understanding the mysterious force shaping our cosmic destiny. Some of the universe's most violent explosions hold the secret to measuring its expansion, not because they're bright, but because their brightness is eerily predictable. Type Ia supernovae are cosmic bombs with a unique quirk. They all detonate with nearly identical luminosity, shining with the power of 5 billion suns at their peak. This consistency makes them the gold standard for cosmic distance measurement, like lighthouses whose true wattage we know by heart. When astronomers spot one of these stellar detonations in a distant galaxy, they can calculate exactly how far away it is by comparing its apparent brightness to its known intrinsic brightness, a method so reliable it's how we first uncovered dark energy's existence. The story begins with a doomed stellar partnership. Type Ia supernovae occur in binary systems where a dense white dwarf siphons material from a companion star. Like a nuclear powder keg, the white dwarf grows until it hits a critical mass, around 1.4 times the sun's weight, triggering a runaway thermonuclear explosion that obliterates it completely. Because this detonation always happens at the same mass threshold, the resulting blast follows a predictable brightness curve, peaking before gradually fading over weeks. This uniformity is what makes them standard candles, celestial yardsticks that let astronomers measure vast cosmic distances with confidence. In 1998, two teams of researchers used these supernovae to hunt for subtle changes in the universe's expansion rate. They expected to find distant supernovae appearing slightly brighter than predicted, suggesting expansion was slowing due to gravity's pull. Instead, they got a shock. The supernovae were dimmer, meaning they were farther away than anyone anticipated. The only explanation, space itself was stretching faster than it should, as if some invisible force was pressing on the cosmic accelerator. That force, of course, was dark energy, and its discovery turned cosmology upside down. What makes Type Ia supernovae so indispensable is their visibility across mind-bending distances. While other standard candles like Cepheid variables fade into obscurity beyond a few tens of millions of light-years, Type Ia explosions can be spotted billions of light-years away, letting us probe expansion rates deep into the universe's past. Modern surveys like the Dark Energy Camera and upcoming projects like the Vera Rubin Observatory scan the skies nightly, hunting for these cosmic flares to map dark energy's influence across cosmic time. Yet these stellar bombs aren't perfect. Dust between galaxies can dim their light, mimicking greater distances, while slight variations in explosion mechanisms introduce tiny uncertainties. That's why astronomers cross-check supernova data with other tools like Baryon acoustic oscillations to build a bulletproof case for cosmic acceleration. Despite these challenges, Type Ia supernovae remain our most visceral evidence that the universe isn't just growing. It's doing so at an ever-increasing pace, driven by a mysterious force we've only begun to comprehend. Each new explosion we catalog is another data point in the grand puzzle of dark energy, another flicker of light illuminating the fate of the cosmos. Cosmologists have a guiding rule so fundamental, it's almost a philosophical stance: the universe, on the largest scales, looks the same no matter where or which way you observe it. Known as the cosmological principle, this idea of homogeneity and isotropy suggests that if you zoom out far enough, the cosmos resembles a perfectly mixed batter, with galaxies sprinkled evenly in every direction. This assumption isn't just poetic, it's the backbone of modern expansion calculations, allowing scientists to treat the universe as a smooth, expanding fabric rather than a chaotic jumble of uneven structures. Without this principle, every measurement of redshift or dark energy would become a nightmare of variables, like trying to predict the weather on a planet where every mountain and valley defies the laws of physics. But here's the catch: what if the universe isn't as uniform as we think? Recent observations have thrown subtle wrinkles into this tidy picture. Take the mysterious Hubble tension, the disagreement in expansion rate measurements which some theorists argue could stem from violating the cosmological principle. Imagine the universe as a loaf of raisin bread where raisins represent galaxies. The cosmological principle assumes the dough rises evenly, but if some regions contain more raisins or expand faster, our calculations could be off. Evidence for this comes from peculiar large-scale structures, like the baffling cold spot in the cosmic microwave background or the sprawling Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years, far larger than homogeneity should allow. These anomalies don't outright disprove the cosmological principle, but they hint at cracks in its foundation. One provocative theory suggests we're living near the center of a cosmic void, a vast underdense region that distorts our local measurements of expansion. Others propose that dark energy's strength might vary across space, creating pockets where the universe stretches faster or slower. Even the distribution of galaxy clusters shows curious asymmetries, with one hemisphere of the sky appearing slightly denser than the other. Yet despite these quirks, the cosmological principle remains indispensable. It's the reason we can use equations like Hubble's law without accounting for every galactic neighborhood individually. The real question isn't whether the principle is perfect, but how much deviation we can tolerate before our models break. Future telescopes like the Euclid Space Observatory aim to map the cosmos in unprecedented detail, searching for hidden patterns that might force us to tweak or even overhaul this cornerstone of cosmology. For now, the universe's apparent uniformity is the best compass we have, even if its needle occasionally wavers. The universe isn't just expanding, it's stretching unevenly, with vast cosmic voids swelling faster than the dense filaments of galaxies threading between them. Picture the cosmos as a loaf of rising sourdough, where air pockets expand more rapidly than the dough itself. These voids, some spanning hundreds of millions of light-years, are nearly empty, just sparse clouds of hydrogen and the occasional drifting galaxy, while the filaments are packed with galaxy clusters, dark matter, and supermassive black holes. This stark contrast in density creates a breathtaking cosmic web, a labyrinth of emptiness and structure that reveals how dark energy's push isn't uniform. Voids act like cosmic accelerators, with their low density offering little resistance to dark energy's repulsive force. Without the gravitational pull of massive galaxy clusters to counteract it, space within voids stretches more freely, as if the fabric of reality itself is thinner there. The BAOs void, one of the largest known, spans 330 million light-years yet contains just 60 galaxies, where a region that size should hold thousands. Light passing through such emptiness gets stretched to longer wavelengths, a phenomenon called the integrated Sachs-Wolf effect, subtly altering the cosmic microwave background and leaving fingerprints of these growing voids. Meanwhile, the filaments like the massive Laniakea supercluster our Milky Way calls home resist expansion through sheer gravitational might. Imagine a tug-of-war between dark energy's push and gravity's pull. In dense regions, gravity wins, slowing expansion locally while the universe at large speeds up. This dynamic shapes the cosmic web, sculpting it into a delicate balance where voids balloon and filaments strain to hold their structure. Over billions of years, this disparity will grow more extreme, with voids eventually swallowing entire galaxy clusters as their boundaries stretch beyond visibility. What's astonishing is how this bubbly structure emerged from near-uniform beginnings. Tiny quantum fluctuations in the early universe, amplified by inflation, seeded regions where matter clumped slightly more or less densely. Over eons, gravity drew matter into filaments, leaving behind voids that dark energy would later pry open. Modern simulations, like the Dark Sky Project, recreate this evolution with eerie accuracy, showing how slight initial differences snowball into the universe's vast, honeycomb-like architecture. Yet the story isn't just about structure, it's about time. Light from galaxies perched on the edges of voids arrives slightly redshifted compared to light from filament galaxies at the same distance, a telltale sign of faster expansion in emptier regions. Astronomers use this to map dark energy's influence, probing whether it behaves differently in voids versus clusters. Some theories even suggest voids might hide clues to modified gravity, challenging Einstein's relativity on cosmic scales. Whether voids are cosmic anomalies or dark energy's purest expression, their silent growth is reshaping the universe one expanse at a time. While the universe's expansion is sending most galaxies hurtling away from us into oblivion, there's a cosmic exception unfolding right in our cosmic backyard, the inevitable collision between our Milky Way and the Andromeda Galaxy. These two spiral giants, along with about 80 smaller galaxies, form what's called the local group, a gravitationally bound family immune to the stretching of space on larger scales. Think of it like a tightly knit group of friends holding hands in a crowd that's rapidly dispersing no matter how fast everyone else moves away. Your little circle stays intact. Here's why this is happening. Dark energy's repulsive force only dominates over vast distances where gravity's pull becomes weak. But within the local group, galaxies are close enough that their mutual gravitational attraction overpowers the universe's expansion. Andromeda, currently 2.5 million light-years away, is actually racing toward us at about 110 kilometers per second, set to collide with the Milky Way in roughly 4 billion years. When that happens, the two galaxies will merge in a slow-motion dance, their stars swirling together like two flocks of birds merging mid-flight. But while our local group remains bound together, the rest of the universe tells a far lonelier story. Galaxies beyond our local neighborhood are being carried away by expanding space faster than light can bridge the gap. Over time, these distant galaxies will redshift into invisibility, their light stretched beyond detectable wavelength. Future astronomers in the Milky Way Andromeda hybrid galaxy will peer into the sky and see only darkness where vibrant cosmic cities once shone, a consequence of dark energy's relentless push. This cosmic dichotomy, local collisions amidst universal expansion, reveals an astonishing nuance in how gravity and dark energy interact. Even as most of the universe's structure dissolves into isolation, pockets of bound galaxies will remain, islands of interaction in an ever-darkening ocean of emptiness. The local group's fate is a reminder that the universe's expansion isn't uniform, it's a tapestry of forces, some pulling together what others are tearing apart. Consider a simple question with a mind-bending answer: why is the night sky dark? If the universe is infinite and filled with stars, every line of sight should eventually land on a star's surface, making the entire night sky glow as bright as the sun. This paradox, first posed by astronomer Heinrich Olbers in the 1800s, seems like child's logic, but its resolution reveals one of the most profound truths about cosmic expansion. The solution lies in what expansion does to starlight over vast distances. When light travels through an expanding universe, the stretching of space itself saps its energy, shifting it to longer, redder wavelengths, a process we call redshift. This isn't just a color change, it's a loss of vitality. Photons that started their journey as visible light from distant stars get stretched into infrared, microwave, and eventually radio waves, their energy dissipating like a fading echo across an ever-widening canyon. By the time this light reaches us, it's often too feeble to register against the cosmic background. But redshift isn't the only factor at play. The universe also has a finite age, about 13.8 billion years, meaning light from stars beyond a certain distance hasn't had time to reach us yet. Combine this with the fact that early stars didn't form immediately after the Big Bang, and you have two cosmic shutters dimming the sky, time and energy lost. Even if the universe is infinite in space, it's finite in time, creating observable horizons we can't peer beyond. Here's where it gets even more intriguing. The cosmic microwave background, the afterglow of the Big Bang, is technically the solution to Olber's paradox in its purest form. It's the stretched, chilled remnants of the universe's first light, redshifted so dramatically over billions of years that it appears as faint microwaves rather than visible brilliance. The night sky isn't dark because stars are absent, it's dark because the universe is actively erasing their light through expansion, like a celestial dimmer switch turned low. This paradox-turned revelation underscores a radical truth. The darkness above us isn't empty space. It's a living record of cosmic evolution, bearing silent witness to the universe's relentless growth. Every patch of blackness is crammed with photons too stretched to see, with galaxies whose light will never arrive, with the echoes of creation itself. The night sky's darkness isn't absence, it's evidence, proof that we live in a universe that's not just expanding, but stretching its history thin across the void. Buried in the cosmic microwave background, the oldest light in the universe, lies a chilling anomaly that defies easy explanation. Dubbed the cold spot, this mysterious region stretches over 1.8 billion light-years and registers significantly cooler than its surroundings, as if a cosmic frost has settled across a swath of the infant cosmos. At first glance, such variations might seem unremarkable. After all, the cosmic microwave background isn't perfectly uniform, but the cold spot's temperature dip is so extreme, it appears only once in every 50 simulations of the standard cosmological model. This isn't just a statistical fluke, it's a potential crack in our understanding of universal expansion. One leading theory suggests the cold spot could be a prehistoric relic, an imprint from a collision between our universe and another bubble of spacetime in the multiverse. Picture two soap bubbles brushing against each other, their surfaces briefly deforming before parting ways. If such a collision occurred in the universe's earliest moments, it might have drained energy from that region of space, leaving behind a cold scar. While this idea ventures into speculative territory, it's not pure fantasy. Cosmologists have long theorized that a multiverse could produce exactly this kind of anomaly, and the cold spot's size and temperature align eerily with their predictions. But there's another, equally mind-bending possibility. The cold spot might be a cosmic void of staggering proportions, a vast, nearly empty region where dark energy's grip is stronger than usual. In these underdense areas, photons from the cosmic microwave background lose energy as they climb out of the void's weakened gravitational well, a phenomenon called the integrated Sachs-Wolf effect. The problem: for the cold spot to match observations, the void would need to be so enormous it challenges the cosmological principle, the assumption that matter is evenly distributed on large scales. Surveys like the Dark Energy Survey have indeed found evidence of a sparse supervoid in the cold spot's direction, but its size alone can't fully explain the temperature drop. Critics argue the cold spot might just be an unlikely statistical outlier, a cosmic roll of the dice that naturally occurs in an infinite universe. Yet its persistence across multiple observational datasets, from the Planck satellite to ground-based telescopes, makes this explanation feel increasingly unsatisfying. If exotic physics isn't at play, why does this one region stubbornly refuse to fit the mold? Some theorists have even proposed that the cold spot could hint at a flaw in inflation theory, suggesting the early universe's hyper-expansion wasn't as smooth as we thought. What makes the cold spot so tantalizing isn't just its strangeness, but what it represents: a loose thread in the tapestry of cosmology, one that, if pulled, might unravel hidden layers of reality. Future telescopes like the Simons Observatory aim to study it with unprecedented precision, searching for subtle polarization patterns that could reveal whether it's a void, a multiverse bruise, or something even more extraordinary. Until then, this icy enigma lingers, a silent challenge to our models and a reminder that the universe's expansion story may still hold untold chapters. What if dark energy isn't just mysterious? What if it's downright apocalyptic? Enter phantom energy, a hypothetical variant of dark energy so extreme it could tear space-time apart at the seams. Unlike ordinary dark energy, which maintains a constant density as the universe expands, phantom energy grows stronger over time, like a runaway freight train with no brakes. The more space stretches, the more potent its repulsive force becomes, a feedback loop that could eventually overpower every fundamental force in nature, from gravity to the bonds holding atoms together. The result, a catastrophe cosmologists call vacuum decay, where the very fabric of reality unravels in a cascade of destruction. To understand how terrifying this scenario is, imagine the universe's vacuum isn't empty but filled with an invisible energy field. Think of it as the lowest possible ground state of existence. This vacuum has been stable since the Big Bang, but phantom energy could destabilize it, like poking a needle into a balloon. If the vacuum's energy state suddenly drops to a lower level, it would create a bubble of true vacuum that expands outward at the speed of light. Inside this bubble, the laws of physics as we know them would cease to exist. Protons disintegrate, matter loses its structure, and time itself may no longer have meaning. The scariest part, you'd never see it coming. The bubble's boundary would give no warning before rewriting reality in its wake. The math behind phantom energy hinges on a single variable in its equation of state, represented by the letter W, which must be less than -1. Current observations peg dark energy's W close to -1, but even a slight deviation could push it into phantom territory. Some measurements of distant supernova and quasars hint at values just below this threshold, though the evidence remains hotly debated. If confirmed, it would mean the universe isn't just expanding, it's on a countdown to oblivion. Unlike the gradual isolation of galaxies in standard dark energy scenarios, phantom energy delivers a violent, definitive end. First, galaxy clusters would be ripped apart, then stars, then planets. In the final moments, even atomic nuclei would be shredded as phantom energy's exponential growth overwhelms the strong nuclear force. Theoretically, this big rip could occur in as little as 22 billion years, a blink of an eye on cosmic timescales. Some models suggest vacuum decay could be triggered even sooner if quantum fluctuations create the right conditions, making phantom energy not just a distant threat but a potential sword of Damocles hanging over reality itself. Yet there's a bizarre silver lining. If phantom energy exists, its sheer destructiveness might leave clues long before doomsday. Astronomers are scouring the cosmic microwave background for subtle distortions, while particle accelerators hunt for signs of vacuum instability. Even the behavior of distant supernova could reveal phantom energy's fingerprints if their light shows unexpected dimming patterns. The quest to confirm or rule out this hypothesis isn't just academic. It's a race to understand whether the universe's fate is a slow fade or a sudden, spectacular collapse. For now, phantom energy remains a haunting what-if at the edge of cosmology, a reminder that the universe's expansion isn't just a curiosity, it could be the prelude to its undoing. What if everything we think we know about the universe's expansion is skewed by our cosmic address? That's the startling question at the heart of the Hubble bubble hypothesis, a provocative idea suggesting we might be living inside a vast, underdense region of space, like a single raisin in an otherwise empty pocket of rising bread dough. If true, this local void could be tricking us into overestimating how fast the universe is expanding, turning one of cosmology's biggest puzzles into a simple matter of perspective. Here's how the illusion would work. In an underdense bubble, there's less gravitational pull from surrounding matter, allowing space within it to expand slightly faster than the universe at large. When we measure nearby supernova or galaxies to calculate the Hubble constant, the rate of cosmic expansion, we'd naturally get a higher value simply because our local environment is stretching more aggressively. Meanwhile, measurements based on the cosmic microwave background, which reflects the universe's overall behavior, would show a slower, more sedate expansion rate. Suddenly, the infamous Hubble tension, the mismatch between these two methods, isn't a flaw in our physics but a cosmic zoning error. The evidence for this hypothesis is tantalizing but incomplete. Surveys of galaxy distributions reveal that our Milky Way sits in a modest void, part of the local sheet, a flattened arrangement of galaxies surrounded by emptier regions. Some studies estimate this underdense zone spans roughly 200 million light-years, with matter density about 20% lower than average. That might not sound dramatic, but in cosmology, even small deviations can have outsized effects. When researchers simulate expansion rates from inside such a bubble, the predicted Hubble constant values align suspiciously well with the higher measurements from supernova, hinting that our cosmic neighborhood might be the ultimate unreliable narrator. Critics counter that the void would need to be improbably large or deep to fully explain the Hubble tension. After all, if we're in a bubble, its edges should leave subtle imprints on the cosmic microwave background, distortions that haven't been conclusively detected. Others argue that even if a local void exists, its influence on global expansion measurements should be negligible. Cosmic expansion is supposed to be uniform on the largest scales, no matter where you observe from. Yet the Hubble bubble hypothesis gains traction because it offers a low-stakes solution. No new physics, no exotic dark energy tweaks, just a simple correction for our unlucky seating arrangement in the cosmos. The stakes here are deceptively high. If the Hubble bubble is real, it means dark energy might be weaker than we think, and the universe's expansion less volatile. But if it's not, the tension between measurement methods points to something far more revolutionary, a gap in our understanding so profound, it could rewrite the rules of gravity or particle physics. Future galaxy surveys like those from the Vera Rubin Observatory aim to map cosmic structures in unprecedented detail, searching for voids deep enough to explain the anomaly. Until then, this hypothesis remains a fascinating reminder that sometimes the universe's biggest mysteries aren't about what's out there, but about where we're standing when we look. What if the very fabric of empty space holds the key to dark energy's secrets? Beneath the apparent stillness of a vacuum, quantum physics paints a chaotic picture, a seething sea of virtual particles popping in and out of existence so fast we can never directly observe them. These fleeting fluctuations aren't just theoretical oddities, they carry real energy, and some scientists believe they could be the hidden engine driving the universe's accelerated expansion. But here's where things get weird. When theorists calculate how much energy these quantum fluctuations should contribute, the result is a number so catastrophically large, it's been called the worst prediction in physics. The math is staggering. Quantum field theory suggests the vacuum's energy density should be around 120 orders of magnitude. That's a 1 followed by 120 zeros greater than what we observe dark energy to be. If this were true, the repulsive force would have ripped apart atoms before they even formed, making life impossible. The discrepancy is so vast, it's like calculating the weight of a mountain based on the rules of physics, only to step on a scale and discover you weigh less than a feather. This colossal mismatch hints that either our understanding of quantum fields is incomplete, or some mysterious cancellation mechanism is at work, fine-tuning the vacuum's energy to near zero. One radical solution comes from string theory, which proposes a multiverse where countless universes exist with different vacuum energies. In this scenario, we simply occupy the rare universe where the numbers improbably balance, allowing galaxies and observers like us to exist. Critics argue this explanation is unsatisfying, bordering on philosophical surrender. Others suggest dark energy might not be the vacuum's raw energy but something subtler, a dynamic field called quintessence which evolves over time. Unlike a static cosmological constant, quintessence could have interacted differently with the early universe, potentially explaining why its effects only dominate now. The irony is palpable. Quantum fluctuations, which seem too weak to notice in the lab, might shape the entire cosmos, while their calculated strength would obliterate reality if unleashed unchecked. Future experiments like the dark energy spectroscopic instrument aim to test whether dark energy's density changes over time, offering clues about whether it's tied to quantum vacuum or something even stranger. For now, this worst prediction stands as both an embarrassment and a beacon, proof that somewhere in the void between quantum mechanics and cosmology lies a revelation waiting to rewrite physics itself. What if the speed of light, nature's ultimate speed limit, wasn't always constant? This isn't just wild speculation. It's a radical idea that could rewrite our understanding of cosmic expansion. Some physicists propose that in the universe's earliest moments, light traveled faster than today's 300,000 kilometers per second. This theory, called variable speed of light cosmology, suggests that a higher light speed during inflation could solve puzzles the standard model struggles to explain, like why distant regions of space have identical temperatures despite never having been in contact. The logic behind this is deceptively simple. If light moved significantly faster in the past, information and energy could have spread across the infant universe almost instantly, smoothing out temperature differences before inflation locked them in. Think of it like trying to evenly mix paint in a bucket. If your stirring spoon moves faster, the mixture becomes uniform more quickly. Proponents argue this tweak eliminates the need for inflation's hyperexpansion, offering an elegant alternative where the speed of light itself did the heavy lifting. Challenges to Einstein's sacred constant don't stop there. If light speed was higher, it would alter how we interpret redshift measurements, the very foundation of expansion rate calculations. Distant galaxies might not be as far away as we think, subtly shifting our estimates of dark energy's influence. The most controversial versions of this theory even suggest that light speed could have changed during specific cosmic epochs, leaving imprints in the cosmic microwave background or the distribution of quasars. Of course, tampering with nature's most famous constant is no small claim. Critics point out that varying light speed would send shockwaves through physics, undermining everything from nuclear reactions to the precision of GPS satellites, all built on light's unwavering pace. Yet the theory persists because it dares to ask a profound question. Are we mistaking cosmic clues by assuming today's laws have always ruled? Until we find definitive proof, perhaps in subtle anomalies in ancient starlight or gravitational waves, the speed of light's constancy remains both a cornerstone of physics and a tantalizing loose thread. Hidden in plain sight, there might be a cosmic anomaly so vast it reshapes our entire understanding of the universe's expansion, a staggering void spanning 2 billion light-years, with our Milky Way floating somewhere near its center. Known as the KBC void, named after scientists Keenan, Barger, and Cowie who identified it. This mind-bending expanse of near emptiness is the largest known structure of its kind, a bubble of underdense space where galaxies are conspicuously sparse. If confirmed, its existence would upend one of cosmology's core assumptions, that the universe is uniformly smooth on the largest scales. Here's why this void is so revolutionary. According to the standard model, matter should be distributed fairly evenly across the cosmos, with only minor fluctuations. But the KBC void defies that expectation, boasting a matter density roughly 20% lower than the cosmic average. To put that into perspective, imagine a balloon with most of its air clustered in one hemisphere, except in this case, The balloon is the observable universe, and we're sitting in the underinflated half. This isn't just a curiosity. It could explain why measurements of the Hubble constant, the rate of cosmic expansion, don't agree. If we're inside a giant void, space here would stretch faster than in denser regions, skewing our local observations. The implications ripple outward. If the KBC void is real, it means dark energy's influence might be weaker than we think, since part of the apparent cosmic acceleration could just be an illusion created by our lopsided vantage point. It also raises thorny questions about the cosmological principle, the idea that the universe looks roughly the same everywhere. A void of this scale shouldn't exist under standard models, yet surveys of galaxy distributions keep hinting at its presence. The cold spot in the cosmic microwave background, a mysterious chill in the afterglow of the Big Bang, lines up eerily well with the void's proposed location, as if the universe left us a breadcrumb trail of clues. But not everyone's convinced. Critics argue that such a colossal void would need impossibly precise fine-tuning to align with our position so perfectly. Others suggest alternative explanations, like exotic physics or even light-bending distortions from unseen structures. The debate hinges on better data. Future telescopes like the Vera Rubin Observatory could settle the argument by mapping galaxy distributions with unprecedented precision. What makes the KBC void so tantalizing isn't just its size, but what it represents, a crack in the foundation of cosmology. If our cosmic address isn't as ordinary as we thought, it means the universe's expansion story might need a dramatic rewrite, one where the void around us isn't empty space, but a hall of mirrors reshaping everything we see. Imagine two ultra-dense neutron stars locked in a death spiral, circling each other hundreds of times per second before colliding in a cataclysm so powerful it shakes the very fabric of space-time. These violent mergers don't just produce light, they generate gravitational waves, ripples in the cosmic pond that travel across the universe at light speed. And here's the game-changing part. These waves carry precise information about the distance to their source, acting as cosmic standard sirens that could help solve the Hubble tension once and for all. Unlike traditional methods that rely on interpreting starlight, gravitational waves give us a direct measurement of how far a merger occurred. The physics is breathtakingly elegant. As the neutron stars orbit closer, the frequency and amplitude of their gravitational waves signal increase in a predictable pattern. By analyzing this crescendo, scientists can calculate the system's intrinsic brightness, how much spacetime it actually warped, independent of redshift or intervening dust. Compare that to the signal's observed strength when it reaches Earth, and voila, you get a clean distance measurement spanning millions of light years. The real magic happens when we pair this with electromagnetic observations. When neutron stars collide, they often produce a kilonova, an explosive fireworks show of gamma rays, X-rays, and visible light. By identifying the host galaxy of this flare and measuring its redshift, astronomers gain both the distance from gravitational waves and recession velocity from light in one cosmic package. This two-pronged approach cuts through the calibration uncertainties plaguing other methods, offering a potentially more reliable Hubble constant. The watershed moment came in 2017 with JWST 70817, the first neutron-star merger detected in both gravitational waves and light. Analysis pegged the Hubble constant closer to the supernova-based fast expansion camp, but with error bars too wide to settle the debate. Future observatories like the Cosmic Explorer and Einstein Telescope will detect mergers 10 times farther away, amassing enough data to shrink those uncertainties dramatically. Some simulations suggest just 50 standard siren events could resolve the Hubble tension, definitively telling us whether the discrepancy stems from measurement errors or new physics. What makes standard sirens so revolutionary is their immunity to cosmic distance ladder assumptions. No need to chain measurements from parallax to Cepheids to supernova. Each merger is a self-contained yardstick. They even probe different cosmic epochs than the cosmic microwave background, offering snapshots of expansion rates across billions of years. But challenges remain. Mergers must be close enough for telescopes to spot their afterglow, and peculiar galaxy motions can muddy redshift readings. As detectors grow more sensitive, these space-time tremors may reveal whether dark energy is truly constant or evolving, a question that could rewrite our cosmic forecast. Every neutron star collision we observe isn't just a fleeting spectacle. It's a ripple from the depths of time, carrying clues about how fast the universe has grown and where it's headed next. At the heart of modern cosmology lies a deceptively simple equation, lambda cold dark matter, or lambdactum for short. This powerhouse model is the mathematical backbone of our understanding of cosmic expansion, stitching together two of the universe's greatest mysteries into a single framework. The lambda represents dark energy, that mysterious force accelerating the expansion of space, while CDM stands for cold dark matter, the invisible scaffolding that shapes galaxies and clusters. Together, they form what scientists call the standard model of cosmology, a recipe so precise it can recreate the universe's entire history from the first microseconds after the Big Bang to the sprawling cosmic web we see today. What makes lambdactum so remarkable isn't just its explanatory power, but how few ingredients it needs. Picture baking a cake with just flour, eggs, and sugar, except in this case, the flour is ordinary matter, a measly 5% of the universe. The eggs are cold dark matter, 27%, and the sugar is dark energy, a whopping 68%. With these three components and the laws of physics, the model predicts everything from the cosmic microwave background's temperature variations to the distribution of galaxies billions of light years apart. It's like having a single key that unlocks every door in the cosmic house. But lambdactum isn't just a theoretical triumph, it's survived a gauntlet of observational tests. When scientists simulate the universe using this model, the results eerily match reality. The cosmic microwave background's subtle fluctuations predicted. The way galaxies cluster into filaments and voids nailed it. Even the universe's age, calculated at 13.8 billion years, aligns perfectly with the oldest known stars. These successes aren't coincidences, they're proof that lambdactum captures something fundamental about the cosmos. Yet for all its elegance, the model has glaring gaps. Neither dark matter nor dark energy have ever been directly detected. They're inferred from their gravitational fingerprints. And then there's the Hubble tension, where lambdactum struggles to reconcile conflicting expansion rate measurements. Some theorists argue this discrepancy might hint at new physics beyond the model, like dark energy that evolves over time or interactions between dark matter and ordinary particles. Others suggest tweaks to the model's parameters, like adjusting the Hubble constant or the density of dark matter. What's fascinating is how lambdactum emerged from decades of incremental discoveries. The cold dark matter piece traces back to the 1980s, when astronomers realized galaxies rotated too fast to be held together by visible matter alone. The lambda component was added in the late 90s after supernova observations revealed cosmic acceleration. Like a jigsaw puzzle assembled piece by piece, each observation locked the model into place. But perhaps lambdactum's greatest lesson is humility. It tells us that the universe is dominated by substances we can't see, driven by forces we don't fully understand. The model isn't the final word, it's a working draft continually refined by new data. As telescopes peer deeper into space and simulations grow more sophisticated, lambdactum may yet face revisions or even replacement. But for now, it remains our best map of the cosmos, a testament to how far we've come in deciphering the universe's grand design, and a reminder of how much further we have to go. The cosmological constant problem is one of the most embarrassing puzzles in all of physics, a discrepancy so vast, it makes even seasoned theorists wince. Here's the heart of the issue. When we calculate how much energy should be bubbling in the vacuum of empty space using quantum field theory, the result is a number 10 raised to the power of 120 times larger than what we actually observe dark energy to be. That's a 1 followed by 120 zeros, a value so absurdly huge it's been called the worst theoretical prediction in the history of science. To put that into perspective, it's like predicting an entire ocean's worth of water should fill a teaspoon, but when you measure, you find only a single molecule. This staggering mismatch has haunted physics for decades. According to quantum mechanics, empty space isn't truly empty. It's a seething quantum foam where particle-antiparticle pairs constantly blink in and out of existence. These fleeting fluctuations should collectively generate an immense vacuum energy, creating a repulsive force powerful enough to rip atoms apart before they could ever form. Yet when astronomers measure the actual expansion of the universe, dark energy's influence is tens of orders of magnitude weaker. Why doesn't the vacuum energy we calculate match the reality we observe? One possible explanation is that some unknown symmetry or cancellation mechanism in nature perfectly balances the books, reducing the vacuum's energy to near zero. But even if such a mechanism exists, it would require precision so exact, it borders on the miraculous, like balancing a pencil on its tip for billions of years. Another radical idea comes from string theory, which suggests our universe might be one bubble among countless others in a multiverse, each with different vacuum energies. In this scenario, we simply live in the rare bubble where the numbers coincidentally allow galaxies and life to exist. Critics argue this is less science and more philosophical hand-waving, but it remains one of the few frameworks that even vaguely accommodates the discrepancy. The implications cut deep. If our best theories predict a vacuum energy this wrongly, it hints at a glaring gap in our understanding of quantum fields, gravity, or both. Some physicists speculate that dark energy might not be vacuum energy at all, but something entirely different, like a dynamic field called quintessence that varies over time. Others wonder if Einstein's general relativity might need tweaking on cosmic scales. Either way, the cosmological constant problem isn't just academic. It's a neon sign pointing to uncharted territory in fundamental physics. What makes this problem so fascinating is how it exposes the fragile seams stitching together quantum mechanics and cosmology. The vacuum's energy density isn't some trivial detail. It's the very fabric of reality, and right now, our equations can't agree with our observations. Until we solve this riddle, dark energy remains not just mysterious but a mathematical absurdity. Future experiments like ultra-precise measurements of the cosmic microwave background or lab tests probing quantum vacuum fluctuations might finally bridge this chasm. Until then, the cosmological constant problem stands as both a crisis and an opportunity, a chance to rewrite physics from the ground up. What if cosmic redshift, the stretching of light that proves the universe is expanding, isn't caused by galaxies racing away at all? Enter tired light, a radical alternative that suggests photons lose energy simply by traveling vast distances through space, like marathon runners exhausted from an endless race. Proposed in the 1920s by Fritz Zwicky, this idea challenges the very foundation of modern cosmology, offering a universe that isn't expanding but static, with redshift as an illusion created by some unknown interaction between light and the cosmos. At first glance, it's an elegant solution, no need for dark energy, no big bang, no runaway expansion. But when held up to scrutiny, does it really hold weight? The appeal of tired light lies in its simplicity. Instead of invoking an entire universe stretching like rubber, it suggests that photons, the particles of light, could gradually lose energy as they collide with interstellar dust or interact with quantum fields. Picture a game of cosmic pinball where light particles bump against obstacles during their journey, shedding bits of energy with each encounter. This would mimic the redshift we observe without requiring galaxies to physically move. Some variations of the theory even propose that light ages naturally over time, like a battery draining, though no known physics explains how. Yet the cracks in this idea emerge when tested against real observations. If tired light were true, distant supernovae should appear blurrier than expanding universe models predict, as their light scatters during its long voyage. But telescopes see no such blurring. Supernova images remain crisp across billions of light-years. Even more damning is the cosmic microwave background, the afterglow of the Big Bang. A static universe with tired light can't explain its near-perfect thermal spectrum or the intricate temperature fluctuations that match predictions of an expanding cosmos. Then there's time dilation, a phenomenon observed in distant supernova explosions, where their light curves stretch out longer than expected. In an expanding universe, this makes sense. Space itself stretches the light's wavelength and slows its perceived passage of time. But tired light offers no mechanism to produce this effect. Without time dilation, the theory collapses under the weight of contradictory data. Perhaps the most telling blow comes from Baryon acoustic oscillations, those fossilized sound waves imprinted on the universe's structure. Their precise spacing aligns perfectly with expansion models, but makes no sense in a static universe where space isn't stretching. Even attempts to retrofit tired light with new physics, like photons interacting with hypothetical dark particles, fail to explain why all these independent lines of evidence point unanimously toward expansion. That's not to say tired light hasn't evolved. Modern variations like plasmonic decay or gravitational redshift in fractal space try to address these gaps with exotic mechanisms. But each tweak adds complexity without matching the explanatory power of lambda cold dark matter. The theory persists less as a rival to mainstream cosmology and more as a philosophical counterpoint, a reminder to question assumptions, even if the answers still lead us back to an expanding, accelerating universe. In the end, tired light's greatest value may be its role as a stress test for cosmology. By probing its weaknesses, scientists reinforce the robustness of the standard model. Every failed alternative tightens the noose around the truth. The universe isn't just expanding, it's doing so in ways that continue to surprise us, defying simple explanations and demanding ever deeper curiosity. One day, far in the future, the universe will play the ultimate magic trick. It will make nearly all evidence of its own existence vanish. Imagine an astronomer in 100 billion years peering through a telescope from a merged Milky Way Andromeda galaxy. Where we see a sky glittering with billions of galaxies, they'll see only darkness. Not because the stars have died, but because the relentless expansion of space will have carried every galaxy beyond our local group over the cosmic horizon, their light stretched beyond detectability. This isn't just celestial solitude, it's the irreversible erasure of cosmic history, a fate scientists call the end of cosmology. Here's how it unfolds. Dark energy's push isn't just prying galaxies apart, it's silencing the universe's story. As space stretches faster than light can traverse it, photons from distant objects get red-shifted into oblivion. Their wavelengths stretched so long they fade into undetectable radio waves, then nothing at all. The first casualties will be the farthest galaxies, their light frozen in mid-journey, eternally too far for new signals to reach us. Over eons, this vanishing act will creep inward, erasing galaxy after galaxy, until only the gravitationally bound local group remains a lonely island in an ever-darkening void. The consequences are staggering. Future civilizations will have no way to know the universe was born in a Big Bang. No redshift to hint at expansion, no cosmic microwave background to whisper of an explosive beginning. The entire cosmic archive, the evidence we use today to reconstruct 13.8 billion years of history, will be lost. It's as if someone burned every astronomy textbook and smashed all telescopes simultaneously, leaving behind only the stars in Earth's immediate neighborhood. Without clues from deep space, the very idea of an expanding universe might seem like ancient mythology. What's especially haunting is how ordinary physics will conspire to hide the truth. Stars in the local group will still form and die, new planets might host life, but their science will draw wildly different conclusions, measuring the universe's age. Impossible without distant supernova, detecting dark energy, unthinkable when all visible galaxies orbit nearby. The cosmic microwave background, already cooled to near absolute zero today, will be so faint and redshifted it'll blend into the cold void of space. Future scientists could believe they live in a static, eternal universe, never suspecting the titanic drama that came before. This isn't just a thought experiment, it's a slow-motion apocalypse for knowledge itself. The window to understand the cosmos is temporary, and we're fortunate to live in an era when the universe still reveals its secrets, those distant galaxies we observe today. They're cosmic messages from a past that won't be visible forever, like letters fading in a time capsule. Each photon we detect from the edge of the observable universe is a gift from an epoch when the cosmos was still loud enough to be heard. One day, the universe will fall silent, and the Big Bang's echo will be lost to the darkness unless we decipher it now while there's still time. What if dark energy isn't a steady cosmic force but something far more dynamic, a fading whisper or growing roar woven into the fabric of space-time itself? That's the tantalizing premise behind quintessence, a class of theories suggesting dark energy's strength might evolve over time, unlike the unchanging cosmological constant represented by lambda in the Standard Model. Imagine the universe as a car where dark energy isn't just pressing steadily on the gas pedal but occasionally easing up or flooring it, altering our cosmic destiny with each adjustment. The cosmological constant, lambda, is the simplest explanation, a uniform energy density permeating space, unwavering since the Big Bang. Einstein initially proposed it to keep the universe static, later discarding it as his greatest blunder when Hubble proved expansion. Yet after the discovery of cosmic acceleration, lambda was resurrected with a new purpose, to represent dark energy's relentless push. Its constancy is elegant, but some observations hint at cracks in this simplicity. Distant supernova and quasars occasionally deviate from lambda's predictions, as if dark energy's grip was slightly weaker in the early universe. Quintessence offers an alternative, painting dark energy as a dynamic field that ebbs and flows. Named after the ancient fifth element, it could behave like a cosmic thermostat, its strength varying based on conditions. Some models propose it was stronger in the past, driving inflation before fading, only to resurge recently. Others suggest it's gradually weakening, destined to vanish entirely. The most dramatic versions even allow for phantom energy, where quintessence grows more potent over time, culminating in a catastrophic Big Rip. Testing these ideas isn't just philosophical, it's a race against cosmic time. If dark energy's strength changes, its fingerprints should be visible in how galaxy clustering evolves across billions of years. Surveys like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies, hunting for subtle distortions in their distributions that might betray quintessence's presence. Another clue lies in the universe's expansion history. Lambda predicts a specific acceleration curve, while quintessence would bend that curve slightly, like a driver subtly adjusting speed. The stakes couldn't be higher. If lambda holds, the universe faces a slow fade, galaxies vanishing beyond an event horizon, leaving isolated islands of stars. But if quintessence is real, the future could be far stranger. A universe where dark energy's whims dictate whether we end in ice, fire, or something beyond imagination. For now, both models remain viable, locked in a tug-of-war between mathematical elegance and the universe's untidy secrets. Every new telescope pointed at the night sky isn't just collecting data, it's casting a vote in the ultimate cosmic referendum. Deep within the cosmic microwave background, scientists have stumbled upon a baffling pattern so unsettling, they've dubbed it the axis of evil. This eerie nickname refers to a strange alignment between certain anomalies in the primordial universe's afterglow and the plane of our solar system, a coincidence so statistically improbable it defies our understanding of cosmic randomness. At first glance, it sounds like something from a science fiction thriller, but the implications are very real. This alignment could be the universe whispering secrets about physics beyond our current models. The story begins with the cosmic microwave background itself, the oldest light in existence, a snapshot of the infant universe just 380,000 years after the Big Bang. In an ideal, isotropic universe, these temperature fluctuations should be distributed randomly, like static on a television screen. But when researchers analyzed data from the Planck satellite, they noticed something chilling. Large-scale hot and cold spots weren't scattered haphazardly. They seemed to loosely align along a particular axis that, against all odds, roughly coincides with the ecliptic plane, the path the sun and planets trace across the sky. The probability of this happening by pure chance, less than 1 in 1,000. This alignment, first noted in data from the earlier WMAP satellite, was so unsettling that scientists initially dismissed it as an observational flaw. Perhaps instrument noise or foreground interference from our galaxy was skewing the results. Yet even after painstaking analysis and improved measurements from Planck, the anomaly persisted. Some theorists now propose it could hint at a pre-inflationary structure imprinted on the cosmos, a relic from a time before the Big Bang's inflationary epoch smoothed the universe. Others speculate that our solar system might be subtly influencing how we perceive the CMB, like a fingerprint smudging a lens, but the most radical explanations venture into uncharted territory. Could the axis of evil be evidence of a cosmic defect, a crack in space-time left over from a phase transition in the early universe, similar to cracks forming in ice as it freezes? Or does it suggest something even stranger, that the universe has a preferred direction, violating the foundational cosmological principle that no point or axis should be special? If true, it would mean the universe isn't as uniform as we thought, forcing us to rethink everything from dark energy's behavior to the nature of inflation itself. Skeptics argue that human brains are wired to find patterns, even where none exist, a phenomenon called apophenia. They point out that among the thousands of ways researchers can slice and analyze CMB data, some odd correlations are bound to emerge by sheer chance. Yet the persistence of this alignment across multiple missions keeps drawing scientists back. Future experiments like next-generation CMB telescopes with even finer resolution may finally settle the debate. Until then, the axis of evil remains one of cosmology's most tantalizing loose ends, a ghost in the data, hinting that our universe might be stranger and less random than we ever imagined. Even the greatest scientific minds can stumble when confronted with the universe's mysteries, and Edwin Hubble was no exception. The man whose name now graces our most famous space telescope initially made a colossal error in calculating the expansion rate of the universe, overestimating it by a factor of 7. The culprit, a simple but devastating mix-up between two types of stars used as cosmic yardsticks, the Cepheid variables. Here's how it happened. In the 1920s, Hubble relied on Cepheid stars that pulsate with a brightness directly tied to their pulsation period to measure distances to nearby galaxies. The longer the pulsation period, the more luminous the star, allowing astronomers to gauge how far away they were by comparing their apparent brightness to their known intrinsic brightness. But there was a catch. Cepheids come in two distinct flavors. Type I Cepheids, found in younger stellar populations, are about 4 times brighter than their type Roman II counterparts, which belong to older star systems. Hubble, unaware of this critical distinction, treated all Cepheids as if they belonged to the dimmer type Roman II category. This mistake led him to severely underestimate their true luminosity and consequently overestimate their distance. The domino effect was staggering. Since Hubble's law links a galaxy's distance to its recession velocity, his miscalculated distances implied the universe was expanding at a breakneck 700 kilometers per second per megaparsec, a rate that would make the cosmos impossibly young, barely 2 billion years old. That contradicted even the geological evidence on Earth, where scientists already knew certain rocks were older than Hubble's entire universe. For years, this discrepancy haunted cosmology, casting doubt on the Big Bang theory itself. The resolution came decades later thanks to astronomer Walter Baade. During World War II blackouts, he used the Mount Wilson Observatory under dark skies to re-examine Cepheids in the Andromeda Galaxy. His keen observations revealed the two distinct populations, correcting Hubble's error and slashing the expansion rate to a more plausible value. Later refinements, especially from Alan Sandage, further honed the number closer to the modern estimate of around 70 kilometers per second per megaparsec. What's fascinating isn't just the error, but how science self-corrects. Hubble's oversight wasn't carelessness, it was a reflection of the limited tools and knowledge of his era. With no way to discern the two Cepheid types, his miscalculation was almost inevitable. Yet this very mistake underscores the iterative nature of discovery. Each generation builds on the last, chiseling away at uncertainty until the true shape of reality emerges. Today, as we grapple with the Hubble tension, modern discrepancies in expansion rate measurements, we're walking the same path Hubble once did, proving that even wrong answers can light the way toward deeper truths. Buried in the vast cosmic web of galaxies lies a ghostly imprint, a whisper from the dawn of time stretching nearly 500 million light-years across. This relic, known as the Sound Horizon Scale, is the universe's most precise measuring tape, etched into the distribution of matter during the first 380,000 years after the Big Bang. Back then, the cosmos wasn't silent, it was a roaring sea of plasma, a dense soup where particles jostled like molecules in boiling water. Photons and baryons, the building blocks of ordinary matter, were locked in a cosmic tug of war, with gravity pulling them together while radiation pressure pushed them apart. This push and pull created oscillations, rhythmic waves of compression and rarefaction that rippled through the infant universe at nearly 2/3 the speed of light. When the universe finally cooled enough for atoms to form, releasing photons as the cosmic microwave background, these waves froze in place like grooves in a vinyl record pressed into spacetime itself. The maximum distance a sound wave could travel before that moment, about 490,000 light-years in today's expanded universe, became a permanent cosmic signature. Today, we see its echo in the way galaxies cluster. They're slightly more likely to be separated by this exact scale than any other distance. It's as if the universe left rulers scattered across the sky, each marked with the same unit of measurement. What makes the Sound Horizon so powerful is its immunity to cosmic evolution. Unlike supernova or Cepheid stars, whose brightness can be obscured by dust, this scale depends only on fundamental physics, the speed of sound in the early universe and when it transitioned from plasma to atoms. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing this pattern with astonishing clarity. By measuring how much the sound horizon appears stretched at different cosmic epochs, astronomers can track the universe's expansion history with precision, offering an independent cross-check against supernova and cosmic microwave background data. But the sound horizon isn't just a static relic, it's a time capsule. When we observe galaxies separated by this scale today, we're seeing the end result of a chain reaction that began in the universe's first second. Tiny quantum fluctuations amplified by inflation seeded regions where matter was slightly denser. Sound waves then sculpted these overdensities, piling up galaxies at predictable intervals like beads on a string. The most ambitious mapping projects, like the Dark Energy Spectroscopic Instrument, are now using this phenomenon to probe dark energy's nature, whether its strength has changed over billions of years or remains constant. The beauty of this cosmic yardstick is its universality. No matter where you look toward ancient quasars or relatively nearby galaxy clusters, the same scale persists, a silent witness to the universe's explosive birth. Future telescopes will extend these maps deeper into space and further back in time, testing whether the sound horizon holds clues to even deeper mysteries, like the universe's elusive curvature or dark energy's ultimate fate. For now, it stands as one of cosmology's most dependable guides, a rhythm imprinted on the cosmos when it was young, still humming beneath the chaos of an ever-expanding universe. When the James Webb Space Telescope peeled back the cosmic curtain to reveal galaxies from the universe's infancy, astronomers expected to see primitive, chaotic blobs, the cosmic equivalent of toddlers taking their first steps. Instead, JWST handed them a gallery of shockingly polished masterpieces. Galaxies from just 200 to 300 million years after the Big Bang, a mere blink in cosmic time, appeared brimming with mature stars, intricate structures, and heavy elements that should have taken billions of years to form. It's like stumbling upon a Renaissance painting in a cave supposedly inhabited by early humans. These discoveries aren't just surprising, they're sending tremors through our understanding of cosmic expansion and the timeline of the universe itself. The crux of the mystery lies in the speed of galaxy formation. Under the Standard Model, the first stars ignited roughly 100 million years after the Big Bang, coalescing into small, irregular protogalaxies. Yet JWST infrared eyes spotted massive, well-ordered galaxies like GLASS Z13 and Sears 93,316 at redshifts above 13, meaning we're seeing them as they were just 250 million years post-bang. These cosmic metropolises shouldn't exist yet, like finding a skyscraper in the middle of the Stone Age. Their advanced states suggest either galaxies formed at breakneck speeds we can't explain, or our estimates of the universe's age and expansion rate are fundamentally off. One radical explanation flips the script on dark matter. Could these galaxies have formed in dense pockets where dark matter's gravitational pull was unusually strong, turbocharging star formation? Simulations struggle to recreate such rapid growth, even under extreme conditions. Another possibility is that early stars weren't just made of hydrogen and helium, but contained trace heavy elements from even earlier, unseen generations of stars, a scenario that would rewrite the chemistry of the cosmos's first epochs. The most unsettling hypothesis: these galaxies might be older than we think, hinting that the universe itself could be marginally more ancient than the 13.8 billion years we've long accepted. The implications ripple outward. If galaxies matured faster than models predicted, it could mean the universe's expansion history needs recalibration. JWST observations might nudge the Hubble constant into slightly different territory, tightening, or perhaps widening, the Hubble tension. Already, some theorists are exploring whether early dark energy, a hypothetical burst of repulsive force in the universe's first moments, could have briefly accelerated expansion, giving structures more time to form before space stretched further. Others wonder if galactic redshifts are being subtly distorted by unknown physics, making these objects seem farther and thus older than they truly are. What's certain is that JWST has thrown a wrench into the gears of cosmology. Every unexpectedly polished galaxy it finds is a clue and a challenge. Future observations will scrutinize these ancient starlight cities for chemical signatures, rotation patterns, and clustering behaviors that could unlock their secrets. Whether the solution lies in tweaking galaxy formation models, revising cosmic timelines, or discovering entirely new physics, one thing's clear: the early universe was far more sophisticated than we ever dreamed. And with JWST still gazing deeper, the next revelation might rewrite the cosmic story all over again. The universe we observe might just be one bubble in an infinite cosmic foam, a single reality adrift in a sea of other universes, each with its own unique physics, constants, and perhaps even dimensions. This mind-bending idea springs from a theory called eternal inflation, where the rapid expansion of space isn't a one-time event but an endless process, birthing new universes in a cascade that never stops. Picture a pot of water boiling violently, with bubbles forming, merging, and popping, except in this cosmic version. Each bubble is an entire universe, and the boiling never ends. At the heart of this theory lies a twist on cosmic inflation, the brief period of hyper-expansion thought to have jump-started our universe. In eternal inflation, certain regions of space never stop inflating. Instead, they keep stretching exponentially while pockets within them relax into stable states, forming self-contained universes like ours. These bubble universes remain forever separate, their boundaries expanding faster than light can cross the gaps. It's as if the fabric of reality is a growing quilt, with each patch operating by its own rules. Some with stronger gravity, others with no dark energy, and perhaps a few where the laws of physics allow for phenomena we can't even imagine. The multiverse idea isn't just speculative fantasy, it emerged as a natural consequence of inflationary theory. When physicists like Alan Guth first proposed inflation, they realized that under certain conditions the process wouldn't just stop neatly. Quantum fluctuations could create regions where inflation continues indefinitely, spawning new universes in a never-ending cycle. This leads to a staggering implication. If inflation is eternal, then the multiverse isn't just possible, it's inevitable. Our universe, with its finely tuned constants allowing for stars, planets, and life, might be a rare oasis in a vast desert of failed or sterile realities. But how could we ever test such a radical idea? One clue might lie in the cosmic microwave background. If our universe collided with another bubble in the distant past, the crash could have left a bruise, an unusual pattern of temperature variations like the cold spot some researchers believe could be a multiverse relic. Another approach involves hunting for evidence of exotic particles or energy signatures that don't fit our universe's physics, hinting at leakage from neighboring realities. So far, no smoking gun has been found, but the search continues in particle accelerators and deep space observations. The multiverse concept also reshapes how we think about cosmic fine-tuning. Why does our universe have just the right amount of dark energy to allow galaxies to form? In a multiverse, there's no mystery. Countless universes exist with random parameters, and we simply live in one where conditions permit our existence. It's the ultimate example of survivorship bias. We're here because this universe's laws allow us to be. Critics argue this explanation is unsatisfying, even unscientific, since it makes no testable predictions. Yet proponents counter that rejecting the multiverse might mean ignoring the logical extension of our best cosmological models. What's truly humbling is the scale of this vision. If eternal inflation is real, then our universe, vast as it is, becomes a speck in an unfathomable ensemble. Some bubble universes might last microseconds before collapsing. Others could harbor civilizations far older than ours, their light forever beyond our horizon. And just as our universe accelerates toward isolation due to dark energy, the multiverse as a whole might keep sprouting new realities eternally, a fractal bloom of existence with no beginning or end. Whether the multiverse remains a theoretical playground or becomes accepted science, it forces us to confront the limits of human knowledge. We may never see beyond our cosmic bubble, never know if other universes exist, but the mere possibility stretches our imagination as relentlessly as dark energy stretches the void. And that, perhaps, is the ultimate lesson. The universe's expansion isn't just a physical process. It's a metaphor for the endless frontiers of discovery, always receding, always inviting us to look deeper. We've journeyed through a universe that refuses to sit still, one that races outward faster with every second, stretching galaxies like taffy across the void. From Hubble's groundbreaking revelation that space itself is expanding, to the spine-chilling possibility that dark energy might one day shred reality apart in a big rip, the cosmos has proven stranger than any fiction. Who could have imagined that nearly 70% of the universe is made of an invisible force we can't touch, measure directly, or even fully explain? Or that ancient starlight carries encoded messages in redshift, whispering secrets about how fast the fabric of space is stretching. The deeper we dig, the more mysteries unravel. The Hubble Tension, where two impeccable methods for measuring cosmic expansion refuse to agree, hints at gaps in our understanding so profound they might demand entirely new physics. The eerie cold spot in the cosmic microwave background could be a bruise from a collision with another universe, while phantom energy lurks as a theoretical specter, threatening to tear atoms apart in the distant future. And let's not forget those bafflingly mature galaxies JWST spotted in the universe's infancy, shining like polished gems in what should have been a cosmic dark age. Yet for all we've uncovered, the universe remains the ultimate puzzle box. Dark energy's true nature, the fate of the cosmos, even the possibility of a multiverse, these are questions without answers, frontiers waiting for the next generation of telescopes, theorists, and perhaps even viewers like you to explore. Every discovery peels back another layer, revealing not just new truths but new enigmas. So the next time you look up at the night sky, remember, those twinkling stars are more than just distant suns. They're pieces of a runaway universe fleeing from each other in a cosmic dance we're only beginning to decode. What secrets lie beyond our current horizons? What future breakthroughs will rewrite the story we've told today? One thing's certain: the universe isn't just expanding, our understanding of it is too. And that journey is far from over.